Okay, I would like to thank the organizers for giving me this opportunity. I would like to apologize because I'm not going to give a talk on a strange metallicity. I'm giving a talk with a strange title, but I think you are going to see how there is a connection. So there will be an introduction, which is where I'm going to present actually my own data about T-square thermal resistivity in metals. And the two parts of my talk are about helium-3. So I'm going to discuss most of the time what has been published like for 50 years ago. And people declared victory and left, but I think there are still mysteries. So the first part is about quasi-particle transport, and the second part is about non-quasi-particle transport in helium-3. I hope to, to especially stimulate theorists here to work again on this unsolved mystery. Okay, so let's begin. The reason, I was brought to the thing is that, like many of you, I was believing, and I continue to believe, that you have a Fermi-liquid, your resistivity is going to be described in this simple way, because basically you apply the Pauli exclusion principle, the two electrons which are colliding. And of course, one thing one should recall is that this is something that you cannot see in gold or in copper. You need either a dilute metal or a correlated metal. And basically, about correlated metals, everybody knows that something like UPT3 or strontium ruthenate has a T-square resistivity, but it is worth to mention that this is also what you see in a dilute metal like bismuth or in graphite. This has been measured many years ago. Now, the subject of my talk is thermal transport, and you are going to see in a minute why. And this is more difficult to measure. First of all, you should get rid of phonons, or you should have a very clean metal not to worry about phonons, but this has been done. This is data on tungsten. This is data on cerium, rhodium, indium-5. And so these data actually confirm. Now, the reason I am going to talk about thermal transport is that we don't need umklapp events to understand this. And you are going to see that this simplifies much the analysis. Okay, actually, we brought to this because we have measured this T-square term in different systems. This is the data on antimony. So we were looking at the way the size of the sample is going to affect your prefactor in electrical resistivity and thermal resistivity. Actually, the prefactor of the thermal resistivity doesn't change that much. The prefactor of electrical resistivity does change, and this is actually in agreement with theoretical prediction about the violation of the Wittmann-Franz law in presence of hydrodynamics. But I'm not going to talk about this. I would like to attract your attention. To my knowledge, actually, this table summarizes everything which has been measured about thermal transport in different systems. So the first thing is that you have a downward deviation from the Wittmann-Franz law. So if you compare these two prefactors in proper units, you see that B, which is the prefactor of thermal resistivity, is always larger than A. And this ratio is somewhere between 0.15, this is the lowest ever measured, and the highest is 0.65. So you can talk about the violation of the Wittmann-Franz law, but this is a very, very...
Could I ask you a quick question just to understand what you're saying?
Yes.
You are talking about electronic thermal resistivity.
Yes,
I just want to make sure, because
yes.
That's what I assumed.
Yes.
So there is a subtraction involved somewhere?
In some cases, not all.
So
experimentally, there is a very simple recipe. You put a magnetic field, and you assume that phonons don't care about magnetic field, or if you care, it is about 1%. If you look at antimony, for example, as soon as you put a magnetic field of 1 Tesla, your electrical resistivity blows up by 6 orders of magnitude. So what remains is your phonon thermal conductivity.
So you apply magnetic field, look at the temperature where nothing is changing, and you say below that it's all electronic?
No. So I try. If you are interested, I will give you the recipe. But the recipe is known for 50 years. You put a magnetic field, and you measure your thermal conductivity at 1 Tesla. This is your phonon thermal conductivity, because your electronic thermal conductivity, again, because of the Wittmann-Franz law, has decreased by 6 orders of magnitude. Then you subtract these phonons from electrons, and then you show this.
So there is an assumption that the magnetic field doesn't affect the phonon thermal resistivity.
But
okay, I just wanted to learn what is being done.
Exactly, but this is okay. So anyhow, what I want to stress here is that look at this. We saw that the difference between A and B can be, it is less than 1. can be 7 to less than 2. But the difference between UPT3 and, let's say, tungsten is 4 orders of magnitude. So the rough Widman-Franz law holds. You know, you can take B and think about A. And the reason I'm doing this is that actually we had a discussion last week. There are systems in which we don't understand why there is T-square resistivity. This is strontium titanite. There is no umklap. You still have T-square resistivity. And actually we measure thermal resistivity and we find the same thing. You saw that it was in the table. So there is no need for umklap and we start. Now, here is the connection to helium-3. This is another system in which there is no umklap. Of course, there is no electrical resistivity, but people have measured thermal resistivity, they have measured viscosity, and now the thing is that in that community, people did not plot thermal resistivity in the way I defined it. They measure kappa, which is T-1. This is the Fermi-liquid prediction, and it works, but it is strictly equivalent to what the metal physicists are talking about, means the T-square thermal resistivity, because you take kappa over T because of the Widman-Franz, and you have T-square. And now, the observation, so this is the data by Greywall. I am going to talk a lot about this data, which was the most complicated, let's say, extensive set of study. And one thing is that there is something called the Kadowaki-Woods ratio between the prefactor of resistivity and the specific heat. Now, it was a mysterious, correlation. It is hard to find it from first principles because you don't know how much umklap you have in one case or in another. But if you put it helium-3, now you see that our units are not a micron centimeter per Kelvin square. It is just meter per watt. And this is simply because it should be proportional to h bar divided by f squared divided by kf. And you see that actually helium-3, this is the specific heat of helium-3. This is the KT of helium-3. There is no impurities. In the other guys, you have this slope. And you see that this is scaling. So somehow the Kadowaki-Woods scaling begins to become not only, it is completely understandable because in the case of helium-3, we understand actually where does it come from. This comes from the Fermi-liquid parameters, the lambda parameters of your Fermi-liquid. So this is the first part of my talk. Actually, the whole point is that this has been understood, but it has implications for metal physics and eventually for strange metallicity. So if I plot now Greywall's data in this way, you see that actually he measured thermal conductivity at 0 pressure. He measured thermal conductivity up to solidification. So this is the phase diagram. You have a correlated fermionic system, which was called Fermi-liquid all above. We are going to come back to this in a minute, but what is interesting is that if you are working on, let's say, quantum critical metals, you are not surprised by the fact that the T-square slope is lower when you have weak correlations, and it shoots up as you go towards the solidification. Anderson called this the best Mott insulator we have, the solidification of helium-3. Now, one observation. So from here, I'm going to make a few observations. I'm an experimentalist. Now, the thing about this is that you can extract the scattering time and compare it with experiment. So this has been calculated by Peter Wolf, for example, using, this is the scattering time that you extract from your thermal conductivity and your specific heat, and you compare it with theory. And actually, these guys are lambda parameters. So if you have the lambda parameters of your system, you can explain this. And this was explained. So in the sense that if you take these numbers, you find that this, what I call zeta, is extremely large in the sense that you see h bar EF divided by kBT squared has the dimensions of, inverse of time. So this could be unity, but it is not unity. It is much larger than unity just because the lambda parameters of your Fermi-liquid is very large. So this is in the book by Volhard and Wolfle. They have tabulated all these, numbers, the lambda parameters which give you the mass amplification, but also will give you this dimensionless collision rate. Now the question is, you see, the reason we have such a large value, zeta is 60 is because F1 and F0 blew up to 15 and almost 90 in this case. And then suddenly the system becomes a solid. Here is where I'm going to just make a kind of, a speculation. It's completely, let's say quantitatively, it has not been yet understood why 3.5 megapascal is the right pressure to make this system a solid. But one idea which was already put forward already by Thales in 1965 and Leggett in 2006 is that, you see, there is a particular difference between a quantum liquid and a quantum solid. Helium-3, when it becomes a solid, it is a quantum solid in the way that each atom frequently visits its neighboring sites. But there is a site. So because of this, these atoms are distinguishable. Each atom has a site, and it can wander around that site by visiting the neighbors. In the case of liquid helium, quantum liquid, there is no such site. And this may happen that this number, which is actually the ratio of 2 times the permutation time you need to any fermionic system, it takes some finite time to make the permutation between the 2 fermions, but you have also an interaction time. And actually, the ratio is this number, which can be acceded by experiment. And now the question is that, is this just an accident that 60 is order of magnitude of this happens? Because, if you have 8 neighbors, if you are a body-centered solid, you can visit your 8 neighbors, and each of those neighbors are going also to visit their 7 neighbors, then you are at the moment where nucleation of the solid can happen. Okay, but I don't know. The question is why it is. Nobody knows. It's just the London parameters are very large, and it matches the theory, but suddenly theory ceases to work, and you have a solid. Now, the second observation is that if you look at T-square terms, of course, these are T-square terms which have been measured by electrical resistivity. The only system among all Fermi liquids that we know of in which this number is as large as helium-3 is lanthanum strontium cuprate. This is funny because the mass is not that large. The mass is just 5. But if you look at the T-square number and extract this zeta, it is much larger than, say, UPT3, where the mass amplification can be as large as 100. Is this a coincidence? You can see it in very simple way. If you don't want all this story, you begin by asking yourself, let's plot the Kadowaki-Woods plot for all metallic perovskites. So these are 2 experimentally accessible numbers. The prefactor, you can measure it from resistivity, specific heat here. All these guys are on the same line, and this guy, I'm talking about the Fermi-liquid one at the heavily overdoped side, is clearly out of the range. So is this a coincidence? And of course, in this case, the Fermi surface, even if it is a simple Fermi surface, it has a strong anisotropy, so you cannot make the same. If there is any zeta, it is different for nodal and antinodal quasiparticles. So from here, I go to the second part of my talk, and you may wonder, is there anything called non-Fermi liquid helium-3? Actually, for me, it was a surprise, because I also believe that if there is any Fermi liquid, it could be helium-3. So you see, there is a recent article, 2016, by Tony Leggett, who actually was coming back to helium-3 as a strongly correlated but well understood Fermi liquid. But he has this point that this is only true when you are well below Fermi temperature, your Q is well below QF, and your frequency is much below EF divided by H bar. And of course, the question is, where does it hold experimentally? And his sentence is that in practice, it seems to agree quantitatively with experiment only for T smaller than 100 millikelvin. The degeneracy temperature, if you don't take into account interaction, is 5K. So this is like 5% of the temperature. Actually, as you are going to see, even this is too optimistic. This is the data from a gray wall. So what I showed, the region where kappa is proportional to T1 over T is actually stops somewhere well below 100 millikelvin. So the two questions that I'm going to raise in the rest of my talk is that, first of all, it is not even 5%, it's more like 2%. But anyhow, it does hold the Fermi-liquid prediction. But Grey-Wall made also another observation, which has not been explained since 1984, that actually at high temperature, this kappa is going to behave like to the T to the power 1/2. And well, where does it come from? So the two questions is why the Fermi-liquid regime is so narrow. And now I have a friend, Kostya Trachenko, who is not a quantum physicist, but he knows very well liquids. And well, he has this book, and the whole point is that actually, if you take any liquid, this is, for me, it was very eye-opening because this is metallic sodium, liquid metallic sodium at 1000 degrees Celsius. This is antimony, this is bismuth, all of these are metals, but in the liquid phase, and these are neutron scattering experiments which see phonons. You have phonons, and surprisingly, in many cases, you have a kind of Roton anomaly, which, now, let's, okay, and one thing that we observed, again, accidentally, is that if you take thermal diffusivity or kinematic viscosity of any liquid, you have a minimum. You have a minimum which is actually set by fundamental constants. So this is at very high temperature, as you can see, and these are classical liquids. But let's come back to our quantum liquid. So this is actually thermal diffusivity of helium-3, extracted from specific heat and thermal conductivity. Actually, the data, again, was reported first by Grey-Wall. But what is interesting is that you have a minimum. So here you have your Fermi-liquid regime, where you expect your thermal diffusivity to go down like T to the power of -2. At 0 pressure, at 3 megapascal, you see that you have a minimum, which is slightly different. Now, look at, this is helium-4, and this is hydrogen. So I pick two other fluids with almost the same mass, not exactly. And what is interesting is that you have a minimum. Of course, you are in the classical regime, and the minimum is almost the same. The vertical axis is the same in these two plots. Now, we understand this because at high temperature, you have a classical fluid. Heat propagates thanks to particles, diffusivity decreases, and at some point you are going to hit the bottom. From here on, you are going to have collective excitations. In the case of a quantum liquid, you should go from the other side. You begin with a gas of quasiparticles. And of course, here is where we were thinking about heat is propagating because of quasiparticle transport. But somewhere here, exactly for the same reason that here in the cold side, you have phonons, here you will have some collective excitations, some sound, which is carrying heat. Yes. And the problem now is that, okay, I think you have guessed, you should find a mechanism which is phonon-based in your quantum liquid. Zero sound. No, it has been already predicted. The problem is that actually, if you list all of mechanisms we know about phonon transport in solids, crystals, glasses, or in classical liquids, none of them has a temperature dependence which is T to the power of 1/2. And the thing about zero sound is that you may wonder, okay, it would be very complicated to have a theory of transport, heat transport by zero sound. Most probably this is true, but what is interesting is that people used inelastic scattering to actually, map the acoustic dispersion in helium-3. They found zero sound, and the surprising result is that actually zero sound continues to be there, even at high wave vectors. There is a collective mode, but there is clearly an anomaly, a minimum, a Roton-like minimum around 2 kF. And this is most probably what you would expect. In general, we are familiar with the fact that linear function has a singularity at 2 kF. This is what gives rise to cone anomaly. This is, but the whole point is that can this be the reason we have this heat transport? Actually, I am going to present, this is the end of my talk, in the sense that you can have a very simple way of explaining your thermal conductivity using Landauer's picture. The reason I'm talking about Landauer's picture is that it gives you boundaries on the amplitude. You see, the thermal conductivity divided by temperature, like electrical conductivity, should be set by quantum of thermal conductance times the transmission. So everything which is about the amplitude is here. Your transmission is something which is depends on dimensionality. It sets the units, because here you have something which is watt per Kelvin, and then it depends on the dimensionality, what kind of meters you have. And if you now put the whole idea that what is transmitting heat is a 2 kF sound with an evanescence, with a mean free pass, which is set by the de Broglie length. The inverse of de Broglie length is the thermal fuzziness of your Fermi surface. You get a number. You see, all of this is just really simple three-dimensional fermion system. The only parameter here is m star besides kf. Kf is determined, m star depends on interactions, and you get something as simple as this. If you are interested, I have no time to discuss the connection between this and the Bridgman formula for classical liquids. It's different, but it is linked. And now let's look at the data. So this is the Grey-Wall data in 1984. So what I'm plotting here is kappa divided by T. This is the Fermi-liquid regime. This is where quasiparticles are transporting heat. And now, if I just put the thermal formula, this is what I get. The only parameter here is the mass of helium-3, which is 2.7. The difference is something of over 10% between the experimental data and this. And now, what is more, if I take just the whole data and try to come with a fit which contains these two terms, this is the quasiparticle term, this is the collective mode, the whole set of data, instead of just 2% at the beginning, can be explained. As you know, we have a hole here. Morphy and Mayer did not measure it at constant volume, they measure it at constant pressure. So the experimental situation is not idealistic given the importance of helium-3, but you see that this simple approach seems to work. In the whole temperature range, you have two contributions. One is the quasiparticle contribution, it is a sound contribution. Now, it's very simple, in the sense that the first one we know. The second one is that in a Fermi-liquid, at least in this Fermi-liquid, it seems that the simplest way of explaining the whole thermal conductivity is to explain that there is a sound component. You have an evanescent wave in the real space where the wave vector is only set by the diameter of your Fermi surface, and then you have this evanescence. So this is the end of my talk. So I have three messages, actually. You see, one of the things is that if you look at helium-3, it is a mystery that you have a very simple way of understanding everything because this can be calculated, from Landau parameters. It is large. The question is there an upper boundary too? This is really an open question. And is it a coincidence that this number is what you get in cuprates? In the case of helium-3, we see that we can explain the whole thermal conductivity with a very simple model. Actually, this is surprising by itself, because why one can neglect all other wave vectors? This is what this implies, but we don't know exactly. But then I end my talk. What about metallic Fermi-liquids? How about the same situation in the case of electrons? Thank you for your attention.
Thank you very much. Questions? Yeah, Jörg.
I had that question to you. Okay. So I had exactly that question to you. So is it a coincidence, just a weird coincidence, that like in strontium titanate you have a T-square in the electrical resistivity and also in the heat conductivity? Or do you understand or think you understand there is a relation between that?
Well, this is what you get in all metals. You see, for the same reason, the only difference was, let me come back to this maybe. So we are measuring LSCO for the moment. I have no data yet to show you. But let's say I would be surprised that you see, okay, I should go back to the table I showed you. People understand it is simply because what holds for resistivity should hold for all these guys. This has been measured by many people. Any system you look at, if you find T squared resistivity, electrical resistivity, you should find T squared thermal resistivity. If not, you are violating the Widman-Franz law.
Right. Yeah.
So these two slopes are not similar. And it is, you know, the understanding is that small angle scattering affects electrical resistivity more than thermal resistivity.
The other way around.
The other way, sorry. So the small angle scattering is underrepresented in electrical resistivity.
So what you're saying, there's a commonality between the two things.
Yes,
all,
yes, yes.
But there's some fine-tuning of material parameters that makes it show up also in the resistivity.
Yeah, so the problem is that electrical, you know, we had actually several times this morning people were talking about umklapp. Where does, it is true, momentum is conserved. So two fermions bump to each other. Normally, that doesn't decay your momentum current. Two fermions bump to each other. There is no reason to invoke umklapp. That will make the thermal current to decay. So if you put now the thermal transport on this driver's seat, then the mystery becomes why the Widman-Franz law roughly holds even when you don't have umklapp.
That's still
Okay.
This is my point, yes.
Alex?
I had a textbook question. So this formula that you used for thermal conductivity through specific heat mean free path and velocity for Boltzmann gas. What is that? It's square root of T, correct, for Boltzmann gas?
Sorry, why shouldn't it be true for a,
So this formula is pretty generic, but we can apply it for different temperature regimes, right? So I could think of a Boltzmann non-degenerate limit, and the question is, what is the kappa for non-degenerate limit?
so
then,
first of all,
my naive thinking. Yeah.
First of all, we are always in the degenerate limit. So there are two questions, you know, there are everything. We are degenerate. The degeneracy temperature in helium-3 is 5K. I am not
5K.
applying it above. So I am.
I see. So even this upturn is still well below that.
Yes.
Sorry.
This upturn happens. You know, the Fermi-liquid ceases to be valid at 100 milli-K at best, which are 50 times below the degeneracy temperature.
Okay.
Yeah. Yeah, very nice talk. Have a technical question. I mean, in gases, usually thermal conductivity, like an air heat conduction in the room, is advective. It's due to macroscopic movement of gases, and that macroscopic movement carries heat.
Yes.
Right, and so what you are talking about is heat conductivity in the center of mass frame of the liquid, and that's fine from the theory point of view, but how do you experimentally separate the convective part from the
so I have never done
part?
So just to say that as an experimentalist, I have never done myself thermal conductivity measurements in liquids, but this is the Bridgman formula. So the Bridgman formula was 1923. So we wrote a simple classical formula in which you just need to know the sound velocity, n to the power of 2/3 and kb. R can be somewhere between 2 and 3. Actually, he puts, this is, but this is the Bridgman expression, and this what has been measured. This is, let's say, methanol. This is a liquid. We are at room temperature. And in many systems, it works. Okay, so basically the understanding is that even here, actually, you have a liquid, but you have a phonon, which is almost localized, so it travels of the order of 1 atomic distance. So the simple explanation of this is this. You have a phonon which travels 1 atomic distance, so you get this. This is the, and this is very, very primitive. It works within a factor of 2, to my knowledge, in ordinary liquids. So we are talking about not liquids, not gases, because in gases, actually, you don't have collective modes.
Okay, more questions? Yeah, it is. Yeah. Get the microphone from.
Yeah, so just to make sure, so in this regime where you see the T to the 1/2, is the specific heat still linear in T?
No. Actually, specific heat is has a complex temperature dependence. Again, specific heat becomes linear in T below 20 millikelvin, 15 millikelvin. Above, you have a deviation downward. But you see, the whole problem is that, again, we are even with approach, if you take even a classical fermionic system without interaction, the entropy is going to join somewhere the classical entropy by equipartition. So even the specific heat, so in my understanding, specifically at intermediate temperature ranges, is hard to explain like this with hands. You need to explain the whole entropy, the temperature dependence of entropy.
But experimentally, what happens? Specific heat is linear in T, and then it goes into what?
No, so I can plot it here because I don't have,
Yes,
if you plot C over T,
not sure that everyone sees it, but
it goes like this. So this is 20 millikelvin. So you can say that this is because the mass is decreasing and approaching the mass, but actually this is below what you expect. But if you look at Graybal's paper, he has plotted all this stuff. You can see the plot of specific heat and entropy.
Yes.
Yeah. So you showed us the plot with the square root of T upturn.
Which one? This is
not this one, but the one with the upturn.
So this is the same, but it is kappa. This is kappa over T. This is
my question is.
Previous one, yeah, even before this
one.
Even before this, I guess. Even before this.
This
one.
Yes.
Yeah. So my question is, in what is the dynamic range where you can really see the square root of T?
What do you mean?
The ratio of the largest temperature where if you have a curve that's square root of T over some interval from let's say the smallest to the largest, what's the ratio of?
I don't understand the question.
Well, it's between 100 and 1,000, the ratio 10.
Look, you see.
Well, I mean, at 100, it only sort of approaches this.
Look, you see, this is the data.
He's asking in what temperature range you have this, I guess it's this one, right?
No, because, so what this is why I come back to this, because I plotted the same, I can put the same thing. Grayball stopped at 1K. This is experimental. But other guys, 10 years after, measured it. So here is the data. This is what was measured by people after. You see that this is again 1 T minus 2. This is the same day. So this was Grayball, but these guys measured at saturated vapor pressure. So this is the difference between these two guys is experimental discrepancy because it is not. But you see the trend is the same.
So it's a factor of 3.
It's a wide range.
What do you mean?
A factor of 3.
What is a factor of 3? I don't understand.
You go from 1K to 3K.
Yes, you may. But again, it's 1K out of K. But somebody should do this experiment again with the same technique to see what's happening. And here, actually, the system is going to become, you have the transition to gas. It evaporates. Yeah, it boils. Helium boils at 3.2.
Okay, more questions. Thank you very much. Thank you. Okay, guys.